The next three videos, I think the next three videos are going to be examples of applications of the conservation of energy, which is written here at the top as delta E equals 0. Okay? But remember that delta E equals, I put the EF equals EI in parentheses underneath that because they're really saying the same thing. These two here, the first and second statements here, are really the exact same thing because delta E means EF minus EI, right? That's what delta E means. It means final minus initial. So those two are really saying the same thing. And to remind you also that the total energy is the sum of the kinetic energy and the potential energy. We're going to apply this in a couple of different situations. The first one here has to do with a baseball thing. Okay, we have a batter who hits a home run. Initial speed of the ball is 36 meters per second. We don't know exactly what the direction is. We're not given an angle. It doesn't make any difference. We could find it if we wanted to later, but we don't need it. We know the initial speed is 36 meters per second. The mass of your standard garden variety baseball is 0.15 kilograms, given right there. So the batter's going to hit the ball and then it's going to rise on its arc, but it's not going to hit the ground because it's going to land in the stands 7.2 meters above the ground, above the field. So the final Y position is 7.2 meters. Okay? And what we want to know, the questions are, what is the final kinetic energy of the ball? And what is the final speed of the ball when it is caught by the fan 7.2 meters above the field? That's what we want to know. Okay? What's the final kinetic energy? What's the final speed? Okay? We won't be able to find the angle. Maybe we could. Maybe we don't have enough information. It doesn't make any difference. What I'm asking for here is the speed, not the velocity. What we're given here initially is the speed, not the velocity. So don't worry about direction right now. Okay, so we're going to apply this. And basically what you do when you apply the conservation of energy is you find the final energy, write it out, find the initial energy, write it out, and set the two equal to each other. Now remember, what I'm calling energy here, the book calls mechanical energy. That's just a whole lot of syllables to add. So when I say energy without qualifying it as kinetic or potential, I mean capital E, the total mechanical energy. Okay? And so we find the initial energy EF, we find the final energy EI, and we set them equal to each other and turn the crank. And by turn the crank, I mean do some recreational algebra. So let's do that. What is the initial energy of the ball? Well, it's kinetic, right? And kinetic is always 1/2 mvi squared plus potential. In this case, remember there's only two conservative forces acting. Now this is true, bing, ding, ding. This is true only when conservative forces do work. Okay? And I've mentioned two conservative forces. One of them is gravity. The other one's the spring force, which we're going to come to in another couple examples. Okay? But for now, only gravity is acting on this ball. We're not going to worry about air friction. Only gravity is acting on it, so we can apply this. Okay? So our potential energy here will be gravitational potential energy, because that's the conservative force we're dealing with in this problem. The ball has already left the bat. Okay? And we're not going to worry about what happens after the ball is caught by the fan up in the stands. Okay? So we're only gravity's working. So this is the initial energy of the ball. The final energy of the ball will be 1/2 mvf squared plus mgyf. So this is initial kinetic. This is initial potential energy. This is final kinetic. This is final potential energy. I don't know what that noise was. Oh well, it hardly matters. So initial energy, kinetic plus potential initial. So let's look at these and figure out which, if any of these, are going to be zero. The initial kinetic energy is not zero. We have a mass, we have an initial speed, so that's not zero. How about the initial potential energy? The initial gravitational potential energy is zero because the ball starts off at y equals 0. The way we've drawn our plot, our picture here, the ball starts off at y equals 0. So y sub I is 0, making this whole term 0, right? Since y sub I is 0, right? That makes the whole thing 0. Now let's look at the final kinetic and potential energies, the final ones. Is the final kinetic energy 0? No. When dude catches it out there in the stands, it's moving when it hits his mitt, so it's got some final kinetic energy. Also, it has some final potential energy as well, because it's at a height it's at a height of 7.2 meters, which means it's going to have some potential energy finally also. So the idea now is that we take these two and we set them equal to each other. EF, as advertised here. Okay. Well, final energy is 1/2 mvi squared plus mgyf. That's got to equal the initial total energy, which is simply 1/2 mvi squared. Okay. Wait, this should be F. Can you find the mistake? Find the professor's mistake. That should be a subscript F. Final kinetic energy. Okay, now notice the first thing we're asked for here is the final kinetic energy, which is this whole thing right here. That is K sub F, so we have to solve for that. Okay, that first term there is the final kinetic energy, this term right here. So we can just call that whole term, we can sort of collapse that down into calling it KF, K sub F, and K sub F is going to be equal to 1/2 mvi squared minus mgyf. So all I did there in that line of algebra, watch closely, is I collapsed 1/2 mvf squared into kf because we're asked for what kf is, and that whole thing is kf. So I just substituted in for that plain old kf, right? Just like it was here. It says kf. So that, and then I subtracted mgy sub f from both sides, so I had kf all by itself over on the left-hand side of that equation. Now it turns out that we know all these numbers, right? We know 1/2, we know 0.15 kilograms. We know the initial speed is 36 meters per second squared minus, again, 0.15 kilograms times 9.81 meters per second squared times 7.2 meters. Did that fit? Yes, that fit gloriously. Okay, so all I've done here is to plug in all our numbers, our M, our VI, our M, our G, our YF, all the stuff we're given over here, free of charge, we just plugged in. And when we do that, we get that KF, the final kinetic energy, is 86.6 joules. So we have two significant figures here. So our final kinetic energy is going to be 87 joules. Okay? Now that we know what the final kinetic energy is, it's very easy to find the velocity because we know that Kf is, as it was before, up here, Kf is 1/2 mvf squared, and that's going to equal 86.6 joules. And we can solve that for m v sub f. Okay, we know the mass, so v sub f is going to be square root of 2 times 86.6 joules divided by the mass, which is 0.15 kilograms. Okay. When you solve that for v sub f, that's the expression you get. You plug in your numbers, and Coamo, you get 34 meters per second. So, 34 meters per second. So it's not going quite as fast as it was, right? It was 36 when it took off. Now it's going 34. So it doesn't have as much kinetic energy here as it had there. Where'd that energy go? It went into the potential energy. So the total energy here is all kinetic. It's all kinetic here, but by the time it gets to point F, it is now split between our two buckets. We started off with all of our energy water, all of our energy in the kinetic energy bucket. By point F, some of that kinetic energy has been poured out into potential energy bucket without losing any, but some still remains in the kinetic energy bucket, right? We started off with all kinetic energy, but at the final point here, we have kinetic energy and some potential energy, which means we had to have lost some kinetic energy to fill up some to put any water into the potential energy bucket. We had to lose some from the kinetic energy bucket. That's why the final speed must be less than the initial speed, because the ball is above the ground and has some potential energy there. Okay, so we've lost some kinetic energy but gained the same amount of potential energy in this problem. Okay. Next up, we're going to do another example, sort of a conceptual example, a fun thought experiment that's going to use the same principle of conservation of energy. I'm going to leave that floating up there, our little conservation of energy cloud up there. I'm going to leave it. Okay. So next up, we're going to have a conceptual question about water slides.